Okay, if you are still standing and you want to stay, please find a seat. Okay, hello. We are starting. Welcome to IRTF Open. It's great to see so many of you, and I think we have a super interesting program today, so I think you're in the right place. Yeah, so this is the open meeting of the Internet Research Task Force, and I'm Dirk Kutscher, I'm the chair of the IRTF. And before we start, I'd like to remind you of our Note Well statement. Basically, this refers to IPR. We expect you to notify us in a timely manner if you talk about IPR or if you see any IPR that you know of. Please note that these meetings are recorded, so audio and video recordings are made, and so being in this room, you can consent to that. And the recording will be made available on streaming platforms later. We have a privacy and code of conduct. So the IRTF recently published RFC 9775, the code of conduct. So that also refers to ethics in research and so on. If you're not familiar with that, please check it out. And also be aware of the IETF code of conduct and the anti-harassment procedures that also apply to us here. Okay, and then finally, we are in the Internet Research Task Force, so we are not setting standards, we are doing research. I think this meeting is very obviously about research, you will see. And I'm just giving you a few updates about the IRTF. So we have 16 groups now, that's a lot. So most of them are meeting this week. And so we have a newly proposed research group that's called the Space RG. And so they are meeting on Thursday at 2:30. So space expands to systems and protocol aspects for circumstellar environments. And so you may be aware that there are quite some activities in the IETF about all kinds of space-related protocol developments and so on. So this group here is explicitly focused on broader research issues in this space. And so as a research group, it will also require your input. What are good topics to work on? And so if you're interested in this, really like to invite you to come to that meeting. So I also like to make you aware of some IRTF-related side meetings that take place this week. Some of them already took place earlier today. So Think to Think RG had a discussion meeting. There was a meeting on distributed inference network and semantic inference, and a meeting on AI network. And later today, after this IRTF Open session, there will be a side meeting on ARMOR. So this is about dealing with internet traffic tampering attempts and trying to figure out so what could be done about this. And on Tuesday, so tomorrow, there is a meeting called PAIN-P. And so it's ironically kind of the opposite topic. So ARMOR is trying to avoid like blocking and so on. PNP is like a security effort that tries to apply like modern technology to identify like adversarial traffic and so on. So these are there may be more meetings that have some connection to IRTF research, but these were the ones that obviously mentioned IRTF. And then one more thing. So if you're working in networking research, you probably are way familiar with ACM Connext. So that the conference takes place in Hong Kong in December. And so we are having like one workshop that came out of, let's say, IRTF discussion on internet working challenges for AI. And so that's at Connext in HKUST's Clearwater Bay campus in December. And another heads up, so we're going to have IETF 125 in Shenzhen in March. And so in the last 2 years, I always organized like internet research workshops in the week before the March IETF. And I'm going to do this again. So these are like fairly open research discussion meetings. I think they went quite well. Had lots of many good people, lots of good discussions previously. We haven't really completed the logistics planning, but I'm going to announce that after this week. So, but maybe for now, it will be on Thursday, Friday before the Shenzhen IETF, and so either on the HKSU campus in Hong Kong or Guangzhou, which is next to Shenzhen. Okay, just quickly, we are also offering travel grants through the IRTF, thanks to our sponsors, Akamai, Comcast, Google, and Netflix. So we have had 4 awardees here this week. And so we are moving the deadlines for application to a bit earlier because of visa constraints and so on. So if you are interested in that, the deadline for Shenzhen is November 14th, so fairly soon. We had ANRW, our Applied Networking Research Workshop in July in Madrid, and we are currently preparing the next one that will take place in Vienna in summer. And so Thomas Schmidt and Suresh Krishnan are kindly agreed to be the TPC, the workshop chairs for this. So expect the call for papers in December, and submit all your many papers. And also, so we were having ANRP winner talks today. We also started the next round of ANRP nominations. And so if you have written any good paper that has good relationship to internet research on IETF topics, or if you are aware of any good paper that you have seen in the conference, please nominate it. And so we will also start the selection process in December. And you can find details on the IRTF webpage, where and how to submit. And yeah, thanks to all the committee members who did a great job in creating the program for this year, of which we will see 2 talks today. So today, I'm very happy that we have 2 excellent papers that will be presented. So Jacob Jenisin will present his paper on a formal analysis of SCTP. And then Saksham Agarwal will present his paper on host congestion control. You can find the papers and also the slides for today on our webpage. And in addition to that, we invited Nada Teixeira from Netflix to talk about a paper she published with colleagues earlier And so the title of today's talk is Low Orbit, High Impact, What We've Learned from for Netflix Streaming over Starlink. And I think it fits quite nicely to the new proposed space research group. Okay, and so with that, I'd like to invite Jake Jenessen to start with his A&RP talk. Just a moment. And before you start, let me introduce you.
Okay.
So Jake Jenessen is a first-year PhD student at Carnegie Mellon University, advised by Brian Parno, and a cryptographic auditor at Cure53. He studies formal verification, cryptography, and programming languages with a focus on real-world protocols. He recently completed his undergrad degree in mathematics at Northeastern University, where he was advised by Christina Nita-Rotaru. And now I'm really curious about his presentation. You have the floor.
Yeah, hello. Thank you for the excellent introduction. Today I'll be talking about our formal analysis of SCTP. This work was completed while I was in undergraduate at Northeastern. It was published in Usenix Security 2024. And yeah, this was in collaboration with my undergraduate advisor, Christina, Max, who's a PhD student at Northeastern, and Michael Tuxen, who's in the audience. How do I progress?
Should work. Doesn't? Ah, sorry. I need. No, it works.
Okay, so SCTP stands for Stream Control Transmission Protocol. It is a transport layer protocol that is it's widely used in mostly telecommunications infrastructure. It kind of underpins SMS, 4G, and 5G, and it's also the data channel for WebRTC, which has lots of streaming applications. You know, your favorite video conferencing or chatting application probably uses it, and it's it has some additional features over other transport layer protocols such as TCP. It supports multi-streaming, multi-homing, and it's largely branded as a little more reliable and resilient, more industrial protocol as an alternative to TCP. Most interestingly, instead of a TCP three-way handshake, SCTP has a four-way handshake in order to establish a connection. So how this handshake works in brief is packets carry initialization tags, denoted as I tags, and verification tags, denoted as V tags. Initialization tags are carried by the init and the init-at chunks of the connection establishment routine on the first two messages. And once the initialization tag is agreed upon, it is propagated to the verification tag, which is carried by every other message in the SCTP connection routine. And in SCTP, there exists a bunch of logic to check validity of both the initialization and the verification tag in order to ensure everything with the connection goes smoothly. So in 2021, there was a pretty bad CVE in SCTP that allowed an on-path or off-path attacker to kill any established SCTP connection. Basically, the worse it gets with a protocol like this. So how it worked is an unauthenticated malformed connection initialization packet was sent to one peer in two peers that have already established a connection. And the peer who received the packet says, hey, this packet is malformed, better abort the connection, right? And it sends an authenticated abort to the other peer, closing the connection when it really should not be doing this. So the cause of this CVE was really a composition of events and behaviors. First, an unauthenticated message was processed instead of being discarded. And the resulting abort was authenticated when the message that triggered the abort was not. This was patched in the Linux kernel, but we wanted to understand whether there were any more flaws in the SCTP protocol logic. So we turned to formal methods to do our exhaustive analysis. So we wanted to mathematically rigorously reason about all possible states of the protocol logic. But we kind of observed, like with the state of formal methods tools, that reasoning about protocol state and message handling and denial of service with a on-network attacker does not necessarily align with the standard formal methods tools that are kind of making headway in like the IETF. Like the TLS group like uses Tamarin to do like cryptographic analysis of like the specification there. But we're kind of trying to do a fundamentally different type of analysis. So we select SPIN and Korg for our analysis. Okay, so SPIN is an automated finite state model checker for concurrent and distributed programs. And Korg is an attack synthesizer for distributed systems. So SPIN is a kind of old model checker. It was invented in the 1980s, and it won the 2002 ACM Systems Software Award. And simply, it stands for Simple Promella Interpreter, and Promella in itself stands for Protocol Modeling Language. Promella is a DSL that is not Turing complete, that is used to represent protocols, simply how processes communicate with each other over channels. And what SPIN does is an automatic verifier for finite state and concurrent distributed systems for protocols represented in Promella. And you specify your processes in Promella using linear temporal logic, which is an extension of first order logic with operators that support reasoning about changes in protocol state over time. You get extra operators such as next and always and eventually and never that lets you reason about kind of execution traces of your protocol state.
If you could move a bit to the mic, it's
hard
to hear.
Thanks. And the Korg framework is an implementation of a paper from 2022 that described a theoretical framework for reasoning about network level attacker models in order to automatically synthesize attacks on stateful distributed protocols, right? What it does is it uses model checkers to exhaustively reason about the state space, to reason about a defined network level attacker model. And because we observe that SCTP is kind of this stateful protocol where it's kind of two state machines that are kind of communicating with each other, we see that Korg is kind of well suited for attacking protocols such as SCTP. Korg offers some built-in attacker models. First of all, it has a basic insert attacker model that allows you to reason about being able to insert messages onto the channel, and a replay attacker model, which allows you to reason about an attacker that can replay scene packets onto a channel. The insert attacker model was introduced in the original seminal attacker synthesis work from Max von Hippel. And the replay attacker model was something I wrote for this work. In extension to this, after this work, I wrote up the attacker model gadgets that can drop and reorder messages on channels and do automatic analysis with respect to those. And hopefully that'll be published later this year. So at a high level, how Korg, this attacker synthesis framework works, is you have your correctness properties, which are specified in LTL, and you have your original Promella model for your protocol. And you feed it into Korg along with the chosen channel you want to attack and your attacker model. What it does is it modifies the Promella model, adding the respective gadgets, and feeds that into the SPIN model checker in order to spit out either an attack trace or give you an exhaustive, conclusive search that there are no attacks with respect to the attacker model. And yeah, this process is fully automated because, in fact, the SPIN model checker is computationally decidable. So we construct a beautiful Promella model for SCTP with a toggleable patch for the CVE. You don't have to understand the details of this model at a high level. This state machine is communicating with another symmetric state machine over a channel. So our model captures all internal states. We capture all message handling, all packet validation, and all invalid packet defenses. And we fully capture the connection establishment and the teardown routines, and we capture all unexpected packets. However, we don't capture the full packet structure. We only capture the packets and the packet information that is important for the connection establishment and the connection teardown routines. Because we are primarily interested in denial of service attacks in this work. Similarly, we don't capture the full data exchange routines because we are not concerned with the congestion control mechanisms of SCTP in this work. We don't capture multicast peers, and we don't capture the full list of channel imperfections. So we formalize 10 correctness properties inferred from the SCTP RFC. These were done in discussion with the RFC author, which is easy to do when he's on your research project. And we formalize those properties in LTL. One example is a section from 9.2 of the FCTP RFC. It states once a connection termination begins, both peers eventually reach a closed state. And that is easily representable given the primitives of linear temporal logic, because linear temporal logic gives you primitives such as eventually and next to reason about. So we also define in this work some attacker models within like Korg's insert attacker framework. Specifically for SCTP, we define off-path and replay attacker models, which SCTP is designed to be resistant against. And we also define the evil server and on-path attacker models, which are stronger, which SCTP is not necessarily designed to resist, but we study them in the worst case scenario to understand what can go bad in these scenarios when you have a strong attacker model. And yeah, we formalize all these attacker models within Korg, and we evaluated them to synthesize attacks or determine if SCTP is not vulnerable to attacks in the model. So our main findings with this work is we see we're able to automatically rediscover the CVE, and we proved that the patch that was introduced to fix it does not introduce any new bugs. We proved that SCTP is otherwise secure under an off-path attacker. And we also proved that SCTP is secure under a replay attacker, modulo a minor opportunistic attack. And we also found two textual ambiguities in the RFC, which lead to off-path attacks if misinterpreted. So one of these ambiguous SCTP specifications was 8.5. The idea was that between like the verification tag and the chunk processing and the initialization tag, there was no specified order in which these tags were processed in. And for the different orders, there's two different orders, right? One of these orders we were able to show that these are provably, like when we were able to show that one order or one interpretation was provably secure, and we were able to show that one interpretation was provably insecure, right? And so this should be clarified, right? So we were able to write an errata for the RFC, and it was later verified in March. So very happy about that. And yeah, I guess before I end this talk, I want to say that I'm doing my PhD in formal methods right now. I guess I come from a more programming languages background. I think the tools that exist in programming languages are extremely good nowadays, and I think a lot of great things can be done with these formal methods tools for a community like IETF. Like tools like Lean are obviously really good for mathy specifications. Obviously, Spin is very good for these kind of distributed systems type protocols. ProVerif, Tamarind, etc. are very good for cryptographic protocols. And very recently, like verification of protocol implementations is getting much better in recent years with tools like Verus and Connie, which are Rust verification tools, as well as the work being done on like F-star for verifying like cryptographic primitives. So yeah, if you have any formal methods questions, or whether formal methods can be applied to your project, or any pointers to people in the literature, I can help you. Okay, thank you very much. I guess to conclude, we modeled SCTP, we defined a bunch of respective attacker models, we automatically rediscovered the CVE, and we proved that the patch does indeed work. And otherwise, we proved the SCTP message logic secure, and we modeled different interpretations of specification and ambiguities. And yeah, before I end, I also want to give another thanks to my team, or I guess my collaborators who made this work possible. Thank you.
Thank you very much. Yeah, thanks, Jack. We have time for questions. Please use the queuing system. Makes it easier to identify you.
I didn't do it. Should I do it? Go into it. Hi, Jake. I'm Dave Flanka. Thanks for doing this presentation. It's awesome.
And sorry, we all have to move much closer to the mic.
Oh yeah, it's awesome that you use the formal method to analyze something that's sometimes so informal in the RFCs. I was wondering if you gathered any opinions, or your team did, about either how we might improve the RFC writing process, like our old words like must and should and stuff, adequate for you and your team to read through? Should we be inviting some students to participate? Are they willing? Like, what was that experience like, and what can you give us as guidance in the IETF that might make this more amenable to analysis?
Yeah, I guess before I give you my answer and opinion, I want to say that like this is my first IETF meeting. I'm not like super familiar with like the processes, but I am very familiar with protocol design in general. I think there's like a lot of room to improve like specification and formal methods co-design. I think like the verification of TLS and the evolution of like TLS 1.3 is a very good example how this can be done. I think like if it was my way, like every time like an RFC was produced, maybe there would be like a formal model or something that specifies the security properties, for example, and proves them with respect to some like basic implementation. Like that would be very cool. I think like some programming languages guy once told me that like if there's like software in general is really hard to specify concisely. Like most software nowadays is like integration, right? There's like a subset of software that can be specified like concisely, right? And that's usually like your cryptographic protocols, your distributed system protocols, a lot of the things that IETF works on. Usually like those protocols that you can specify concisely, they like usually the PhD students work on those, and you see a thesis, oh, I verified this in this protocol. Yeah, that's like usually work that PhD students do. And that same professor told me that one PhD student's thesis is a worthy cost to pay. But I don't know, maybe there's a world where students and maybe people from the IETF continually work on that, especially as these tools evolve and become easier to use. Sorry for the long answer.
Hi, Rod Van Meter, Carey University. Thanks. That was a fantastic talk, and it looks like great work. You did a good job of laying out the environment in which you did the testing, but I didn't get a good feel for what the cost for doing this is. Is this something you can do in 10 minutes on a laptop, or does it take a month on a supercomputer?
Like the computational cost of running the models?
Both the computational cost of running the models and also the human cost, how much of your time it takes to do this. Yeah,
so computationally, like the models that currently exist, you can like run it on your laptop, you can verify it. But like in using like a formal methods tool like Spin, you have to like constantly trim the state space and like modify the model such that there is no state space explosion. Because like there were times when I was working on this where like I had to like give it to, you know, a bigger computer and not my like really old laptop, in order to let the state space exhaust and terminate. But we did result in a model that is very, that does concisely represent the behavior we need. I think spin in general is also kind of old, and the techniques are kind of old. So you also might have a better luck with today's tools that are like more computationally efficient. And in terms of human cost, it took me like 2 years to develop all the SCTV models and all the core infrastructure. But then again, I was like an undergrad and I like never touched research before. That was like my first major research experience, was kind of working on this project. So yeah, the 2 years is definitely inflated. Maybe it would take like a good PhD student, I don't know, maybe like a semester of work, if I had to guess.
So it's still a pretty substantial commitment. Good, thanks.
Yeah.
So sorry, I'm asking a question. You had a, you know, this slide with all the different tools in the end. Just wondering, so do you have any concrete ideas? So what could be done next in terms of tooling for the IETF or IRTF? Is there anything that you think is a really good next target?
In terms of tooling, I think like the current state of tooling is really good for expressing protocol designs. Lean is really good at, you know, mathematical specifications. You know, I said this at the end of my talk. The tools for like reasoning about protocol designs are really good if you like know they exist. What's really next is protocol implementations. I think like there's a specification implementation gap between like the behavior of the mathematical specification in abstraction to like the implementation in like Rust or C or whatever. Tools like Veris in Rust do a really good job at kind of bridging this. I think kind of the next step, I mean, it's unclear. I think the IETF does like a lot of protocol design and not necessarily protocol implementation. But you know, maybe like people adjacent to the IETF would be able to pick up like actually constructing verified implementations of the specifications.
Okay, thank you, Antonio.
Yeah.
Antonio Vicente, Cloudflare. I'm not very familiar with formal methods and the tools available for them. I'm somewhat curious about like what kind of pitfalls you might actually run into as you try to like optimize your model. Will you actually be able to actually have like some situation where like you actually like don't get enough flexibility to actually find things because where you actually trim down your space and cannot find some real issues that way?
Good question. So I guess like all formal methods tools kind of deal with this like trade-off between the expressibility of the tool and the automation of the tool. And the biggest problem with formal methods, like as a field, like in my opinion, people will get very mad about this opinion, by the way, is that you have all of these different tools for all of these different like processes and for verifying things of like different levels of specification, of different levels of expressivity with like different levels of automation. So it really takes like trying all these tools and failing, or talking to someone who is inside the field to point you to be like, you're trying to specify this property and you're using this system. You want this in this tool. Because I think it's very easy to get trapped using a tool that's too expressive and the state space is too big and it's not enough automation you want. Yeah.
Next question.
Petr Špaček, ISC. I'm definitely not a researcher. I'm a software developer doing DNS, and I just want to underline what you said about the gap between spec and the actual implementation, because at least in DNS resolver, at least half of the complexity is in the stuff which is not in the spec at all, but it has to be there because it doesn't work without it. Yeah. Basically, it's workarounds for incompatible spec implementations which don't follow the spec and stuff like that. So I'd be really curious what's your thinking about, you know, this monster. Is it like big no-go? Do we first have to go and like try to write actual spec, or is there suitable tool which would help us to find and identify the gaps? Because sometimes you don't even know that there is a gap because the workaround is literally 25 years old and no one remembers that it's there. So it's sometimes we like rip out this piece of code. I don't know what this does. So what happens if I delete this? And then I cannot resolve like Facebook or something. So it's like, I need to put it back, but God knows how it got there and why, So that kind of stuff. So is there a tool which would help us identify the gap between the implementation and spec? That's basically my question.
Good question. For DNS in specific, I don't really have a good answer. I think like there's like differential testing techniques to like, for example, you have like a higher level specification that you just like write that's maybe not absolute versus like your actual DNS implementation, and you want to see whether they align on all possible behaviors. But also, I think like in general, like the PL people, the formal methods people, they'll try to write more informal specifications in like maybe like written English RFC style for their code. I do not know. I don't work in DNS. I don't know if that sort of thing exists for DNS, but usually like how the process goes, oh, there's an informal spec, and then the formal methods people are like, aha, and then they go and formalize it. I think that's kind of how the process goes.
I'm Stuart Cheshire from Apple. Welcome to the IETF. You said this is your first time here.
Yeah.
I highly recommend you take advantage of being here. We're a friendly bunch for the most part. Ask questions, meet people. One example, the reason I came to the microphone, you talked about the mental image you have that we write specs and then kind of throw them over the wall and tell engineers to implement them. And that is how many standards bodies work. One of the interesting things about the IETF is it's very unusual in that regard. The mantra of the IETF is rough consensus and running code. And it's one of the reasons the IETF has been successful for the last 40 years is we don't just write something on paper. We have an idea, we implement it, we come back, we say what worked, what didn't work, we revise the spec, and we do this feedback loop. And it's one of the reasons that IETF protocols generally work, and a lot of the ones they're competing with don't. So there's lots of stuff you can learn while you're here this week about things like that, about the history of protocol design and what works and what doesn't.
Cool, thanks.
Okay, so on that nice comment, let's thank Jake once again. So let's, if someone wants to take a photo, then now's a good time. Oh, right. Well, can you just stand there? Sorry. Not in that group. I'll block it out. Cool. Okay, thank you. Okay. Before we continue, let me move this a little bit to the right. Back to us. Okay, we continue with Saksham, the next prize winner. And if you could start sharing the screen. So the next talk is by Saksham Agarwal about host congestion control. This was a paper at ACM SIGCOMM in 23. And so Saksham is an assistant professor at the ECE department of the University of Illinois, Urbana-Champaign. And he did his PhD at Cornell and his undergrad studies at IIT in Kanpur, India. And he has already won many awards. So he is a recipient of the SIGCOMM Dissertation Award, the Cornell Computer Science Dissertation Award, the SIGCOMM Best Student Paper Awards in 2024 and 2018, the Google Research Scholar Award, the Google PhD Fellowship, and a Cornell University Fellowship. His research interests broadly lie at the intersection of computer networking, systems, and architecture. And, welcome, Saksham, and let me... Right. Okay. So you have to stand really close to the mic. Okay, take it away.
Can I take it with me?
Yeah, sure. So just don't move too much to the left because then the projector is you are then basically.
Hello, everyone. Thank you, Dirk, for the introduction. Really honored and excited to be here. So today I'm going to talk about this exciting new research problem of host congestion. This line of work started a couple of years ago in lab when I was running an extremely trivial experiment. Just an application sending data between a pair of machines directly connected to each other via switch. And we saw an unexpected phenomenon. We saw the sender was, the data sent from the sender was not reaching the receiver. Somehow it was getting lost. And this phenomenon didn't seem to be reported in the networking or OS communities before. So we thought, okay, there might be a bug. But looking at the basically switch telemetry, there was nothing wrong with the switch. And the issue turned out to be much more profound. And since this phenomenon was reproducible, and it was not reported in the community yet, my PhD advisor, Rachit, he reached out to some of his contacts at Google, and turned out even they had, at that time, recently started to see similar phenomenon. So I decided to spend a couple of months there and help them characterize this phenomenon in their production clusters. And to resolve this problem, turns out we had to rethink how we design congestion control protocols, especially in terms of how they interact with the operating systems and even the host architecture. So today I'm going to revisit this journey with you all the way from the initial lab experiments to characterizing this problem in the real world in production clusters and how should we rethink congestion control protocols. Okay, so let's start. So this problem, okay, there's a slight lag. Okay, so this problem was first observed in the context of cloud computing or data centers, where you have distributed applications like data analytic frameworks or ML training applications doing high-speed data transfers across multiple hosts within a data center, right? But the end-to-end path of these data transfers also involves transfers within the server, especially within CPU cores, memory, and peripheral devices like the network interface cards, or NICs for short, right? So I'll refer to this last mile of data transfer within the host as intra-host transfers. Okay, so these intra-host transfers are enabled by something I call as the host network. So let me zoom into this host network for a bit. It is enabled by different kinds of interconnects. One is the processor interconnect, which is used to transfer data among different CPU cores. And then there is this peripheral interconnect, which is used to transfer data from peripheral devices to the CPUs or the memory. And then there is this memory interconnect, which intercepts the read or write requests from peripheral devices or the CPUs and executes them on DRAM. Okay, and the host network is basically the interpolation of all these multiple kinds of interconnects. So when the data comes from the NIC, it goes via all these different interconnects all the way to the memory. Okay, so now traditionally this host network has always provided many desirable properties like latencies of the order of nanosecond scale, ample bandwidth for transfers, and lossless data transfer guarantees, right? So for example, the peripheral bandwidth of these, the peripheral interconnect bandwidth is typically higher than, for example, the NIC bandwidth, and the memory interconnect and processor interconnect bandwidth are even larger than the peripheral interconnect bandwidth. So throughput or bandwidth is never a problem here. right? So the conventional wisdom in the systems and networking community was that for the context of running distributed data center application, this host network typically works as an ideal network, right? So if we think about any data center application, it consists of broadly two kinds of components. One, a network component, which involves transfers across the network between multiple nodes, and a host local component, which involves computations using reads and writes to the local memory, right? So let's consider a simple toy example where we have two nodes, say connected via 100 Gbps link using a single switch, right? And my network component of the application is sending data from the sender to the receiver, right? Now here, typically the throughput of these distributed applications is going to be bound by your NIC bandwidth, right? And your intra-host network bandwidth, your host network bandwidth is larger than the NIC bandwidth. And the latencies of these applications is typically the order of few tens to hundreds of microseconds. So the nanosecond scale latencies of the host network should not impact, right? So basically, is host network an ideal network, right? So let's verify this intuition with a quick demo. Now, if I would have given this talk a couple of weeks ago, a couple of months before, I could have shown you a live demo, but Cornell revoked my VPN access, and I haven't set up my new topology at UIUC yet. But what I'm going to show you is just a screencast of one of my earlier demos. For now, we can just pretend that, okay, it's live. Okay, so the numbers that you see here, let's just pretend they are live, reported from the servers running at Cornell using the same topology that I showed you earlier, two nodes with a single switch, right? Okay, so I'm going to run two kinds of network applications. One is a throughput intensive application, which sends lots of basically large size data chunks over the network. Essentially, I'm using iPerf. And then I'm also using a latency bound network application, which does a ping pong of small size requests, essentially netperf. Okay, so the plot you see on the top left shows the network throughput versus time. Higher value is good. So you can see that as soon as I started the application, we were able to saturate the 100 Gbps link bandwidth. The throughput is 100 Gbps. The plot on the top right shows the tail latency for the network, for the latency bound application for different values of tail from P99 to 99.99. And so lower value is good. And we see that we are getting expected tail latency values of around 100 microseconds. So far so good. This is what we'd expect if there was no congestion happening anywhere in the data path. But now I'm also starting the host local application because that's also an important component of the distributed applications. So what I'll do here is that I'll just run an application which is generating a steady stream of memory reads and writes. Right? It takes a couple of seconds to load up. And now you see something interesting. If you look at the throughput of the network application, it has dropped by more than 50%. To around 45 Gbps now. And if you look at the tail latency, it has increased by several orders of magnitude, right? And interestingly, if you look at the bottom left, it shows the packet drop rate versus time. So we have started to see packets getting dropped somewhere within this topology, which consists of one sender, one receiver. Right? So this is the surprising phenomenon which I was alluding you earlier, right? What's going on? So over the next couple of slides, I'll try to give you some intuition of what we learned. So if you look at the end-to-end data path of these network application, data goes all the way from the memory of the sender host via the host network and the network fabric to the memory of the receiver host. Right? We verified that nothing wrong was happening with the switch. There was no bugs there. Turns out the data was getting queued and dropped at the buffers at the receiver side NICs. So for some reason, the DQ rate from the NIC to the memory was smaller than the arrival rate, right? So even though the host network ideally should provide much larger bandwidth than the NIC, for some reason it was seeing some inefficiencies, right? And it is basically this inefficiency for NIC to memory data transfer, which I refer to as by host congestion, right? And let me try to give you a couple of root causes or examples of why host congestion can be caused, right? One reason is because of contention at the shared memory interconnect. So this memory interconnect is not just used by my network application, data transfer from NIC to the memory, but also by this host local application where CPUs are reading, writing to the memory. So even though my memory interconnect bandwidth is larger than the PCI or peripheral interconnect bandwidth, but when we take into account both the host local traffic and the network traffic together, then the memory interconnect can be contended. Okay. Now, and turns out host congestion can also happen even without the presence of host local traffic because of this another point within the data path, which is used to provide IO memory protection. So most of today's cloud providers use IO memory protection mechanisms to protect against buggy or malicious IO devices. So what this protection mechanism do is they supply the NICs with virtual addresses to perform DMAs, and this there's this address translation device. Some of you might be familiar with IMMUs, which perform this virtual to physical address translation, just like MMUs. And they also have some caches to speed up the translation. And what's happening now is when you have very high-speed IO devices coming up, they tend to keep a lot of parallel in-flight requests, so in-flight translations for virtual to physical address translation, which can lead to these cache misses and contention even at this IO memory protection mechanisms, right? So together, basically contention at these sort of memory interconnect or the IO memory protection mechanisms can lead to these inefficiencies that we see from NIC to memory data path, right? So, okay. Now let me try to give you a bit more detail into what's fundamentally happening, why this contention at these 2 points is leading to this reduction in the achievable NIC to memory throughput, right? So whenever, suppose we have some desired NIC to memory data transfer rate, which is basically the NIC bandwidth, right? To meet this NIC bandwidth worth of throughput, there is a certain amount of latency budget that, okay, there's some lag. There's some latency budget that each NIC to memory transfer must meet. So, and this latency budget is inversely proportional to the NIC bandwidth and directly proportional to some hardware defined parallelism. So to give some intuition, if my NIC bandwidth was very large, package will be arriving very, very fast, right? So your NIC has small amount of latency budget to basically keep up with the required bandwidth. But if your DMA engine or your hardware supports more parallelism, supports more NIC to memory transfers at the same time, then you can basically relax your budget a little bit, right? So the bandwidth and parallelism define my budget. Now, without any host congestion, we see that we are within the latency budget and the NIC is able to transfer the data to the memory at the required bandwidth. But contention at the memory interconnect or this the IO memory protection units can lead to inflation in NIC to memory transfer latencies, right? And once this inflation overshoots the required budget, that's when we start seeing degradation in the achievable NIC to memory transfer rates, right? So effectively, it's nanosecond scale latency inflation, between the NIC to memory transfer latencies, which are leading to this reduction in achievable throughput, which are leading to reduction in degradation in application level performance, right? But it's slightly easier to think about this problem in throughput perspective rather than latency. So for the rest of this talk, we're just going to assume host congestion implies degradation in throughput, but it's useful to keep in mind that it's actually these nanosecond scale latency inflations which are the root cause of this problem fundamentally. Okay. So, okay. So now we know about the host congestion phenomenon. Let's try to just quickly take a look at its impact. We already saw that host congestion in the demo in my small scale testbed already showed around 0.3% packet drops. And when we are running congestion control protocols, and the demo was running DC-TCP as the congestion control protocol. So if you run these TCP, DC-TCP, whenever you see packet drops, it leads to significant reduction in sending rate, which leads to degradation in throughput. And these drops can lead to retransmissions, increasing latencies. Retransmitted packets can get further dropped, leading to timeouts and significant inflation in tail latencies. Right? And this is, and we also verified that same problem also happens when we use hardware offloaded network stacks like RDMA as well. Right? And turns out it was precisely the same problem, which was also happening in Google's production clusters. So the plot that you see on the right-hand side shows a scatter plot of link access bandwidth utilization on the x-axis and packet drop rates at the hosts on the y-axis. Each point shows the intensity of drop rates. Purple color means more intensity. So even after using the state-of-the-art congestion control protocols and network stacks, these hosts in Google's production clusters saw significant drops even when the link access bandwidth was far from fully utilized. Right? Kind of what we also see here. Okay. Right. So why did we see this host congestion problem just now, like a couple of years ago? Turns out it was the technology trends, right? Just to give you some context, okay, so what I'm showing here is the relative trends between the total peripheral interconnect bandwidth within the state-of-the-art servers that year with the total memory interconnect bandwidth, right? So, for example, between 2017, okay, it's this. Slow. Yeah, it's a bit lag. Okay, it will come sometime, but okay. Something's wrong.
That's probably not only host congestion, but some other congestion.
Yeah. Let's see. Let me start again.
Unstable connection to the server, trying to recover it. Okay.
Unstable connection to the server.
Okay. Do you want me to show your PDF? Or we can try again.
Okay, it works now. Let's see. Okay, perfect.
Yes.
Okay, so recovered from network congestion. Okay, so between 2017, when I started my grad school, and 2023, when we kind of just started to see this problem, we saw the peripheral interconnect bandwidth grow from 1/3 of the memory interconnect bandwidth to crossing it for the first time in the history, right? And so what that led to is that it became much more easier for the memory interconnect to be overwhelmed by the network and host local traffic together, right? And the current and the future trends don't look very, it will come, very nice either in terms of this problem. So by 2026, at least from the public data that we have available, the PCI bandwidth might become around 1.5 times the memory bandwidth, suggesting the problem is only going to get worse over time. And after Google, many other cloud providers like Microsoft and ByteDance have already reached out to us, telling that the problem also was happening in their production clusters as well. Okay. So now we know what this problem is and what fundamentally led to this problem. One question comes, okay, so why were the existing network protocols like congestion control not able to perform well for host congestion, right? Before I discuss that, I know a lot of the crowd here already knows a lot about congestion control, but I'll just give a very, very brief primer. So congestion control is like one of the most fundamental problem in Kubernetes networking. The main goal here is to manage these shared network resources like link bandwidth and switch buffers so as to provide high throughput, low latency, and avoid switch buffer overflows for the networking applications. So how congestion control protocols work is these protocols use these congestion signals to detect whether they want to, how they want to respond to congestion. So for example, TCP or its data center variants like DCTCP or Timely use either switch buffer occupancies or measured network delays to as congestion signals. They measure these values with some specified threshold. If they are smaller than the threshold, then they increase the rate at which traffic is injected into the network and reduce otherwise. Okay, so one important thing is that host congestion requires or forces us to fundamentally rethink the congestion control architecture. This is because of two reasons. One is we need to rethink the congestion signals. So traditional congestion control protocols have this implicit assumption that packet queuing or drops happen at the point of congestion. So while this was true for queuing happening at the switch buffers, when host congestion happened, for example, due to contention at the memory interconnect, queuing and drops can happen at a different point, such as my NIC buffers, right? So So basically, so what this leads to is the traditional congestion signals fail to capture the precise time, precise location, and the precise reason for host congestion. That's one thing. So implicitly what's happening is the existing protocols implicitly think that the network begins and ends at the NIC. It looks like there's another burst of congestion coming.
Let's hope for the best.
So the protocols typically assume that the network begins and ends at the NIC.
Thank you. To try again, we probably need to.
Yeah. Connection error to service.
I don't get it yet.
Facing this. The server is currently unable to handle the request. So I'll refresh.
Yeah.
Oh, it says no internet actually. So the Wi-Fi disconnected. So it looks like the Wi-Fi might be.
Yeah, it's the Wi-Fi.
I see.
Yeah, sorry about that.
Okay.
Okay, got it.
Okay. 3, 2, 1.
Okay.
High tail latency. Okay. So traditional protocols assume that the network begins and ends at the neck, but so for them, this congestion is kind of happening outside their view of the network, right? So these signals are not able to capture host congestion. Now, we also need to rethink congestion response. This is because of two reasons itself. One is that the host local traffic, unlike the network traffic, does not employ congestion control mechanisms like TCP. Right? To understand this, let's consider this diagram on the right, which shows allocation of rates for host local traffic and network traffic at certain point. And suppose host congestion triggered at this point, which led to queuing at the NIC buffers and eventually drops. And this will lead to network protocols like TCP kicking in and reducing the rate, sending rate only for the network traffic, right? But the host local traffic can just occupy the leftover resources given up by the network traffic, right? So this is kind of like the problem when TCP and UDP share a common link, and UDP can just occupy the bandwidth, leading to starvation for the network traffic, right? So that's one problem. The other is the time granularity at which the host local traffic and the network congestion control work. So the host local traffic is generated by CPU cores, which are physically located very close to this point of congestion, that is the memory interconnect. And the degree of host congestion can vary significantly at sub-microsecond timescales, right? However, the congestion response is performed at network round-trip timescales, which can be a few tens to hundreds of microseconds in typical data centers, right? So this mismatch can lead to either quite delayed or quite prolonged congestion response, leading to far from optimal performance for applications, right? So we proposed HostCC, a new congestion control architecture for host and network fabric congestion both. The new key fundamental idea in HostCC was this introduction of a congestion response local to the hosts, which was performed at sub-network RTT granularity. Right? So this host local response enables HostCC to, again, revisit this conceptual mismatch of congestion control protocols, which I was talking about. So this allows all of my shared resources. For example, my host network resources are shared between my network traffic and the host local traffic. So host local response allows me to share these local host resources across these competing entities of network applications and host local applications, right? So this kind of revisits the distribution of responsibilities between the network protocols and the OS stacks, right? So if you look at the network protocols like congestion control today, they are used to allocate my network resources, and my host local resources are managed kind of independently by other various components of the OS stack, right? So HostCC's host local response kinds of takes a coordinated approach between my network protocols and my OS stack, right? So this allows my sender to not see starvation because of host congestion, and it allows my receiver to achieve my NIC to memory transfer rate desired by the user, and allow me to reduce the amount of queuing and drops that I see. Right? Okay. So now let's try to understand HostCC's end-to-end architecture. So it basically has three different components. One is the HostCC uses new congestion signals, which are local to the host. We call them host congestion signals. which allow us to precisely capture the time, location, and reason for host congestion. We use these host congestion signals to perform the host local congestion response, which I mentioned in the previous slide. And in addition to these two, HostCC also rethinks the network congestion response, which today use network congestion signals. What HostCC also does is it also uses host congestion signals along with network congestion signals to perform an end-to-end congestion network congestion response. The key idea there is the sending rate for the network sending rate should be decided by the minimum of the network fabric bottlenecks and the end-to-end host bottlenecks. Right? Okay, so now I'll go into relevant details for each three of them one by one. Let's start with host congestion signals. Okay, so to understand HostCC's congestion signals, we'll have to go slightly deeper into the host architecture. Okay, so whenever a new IO request comes at the NIC, these requests go via the peripheral interconnect to this component called an integrated IO controller, or an IIO, where they occupy some, they stay enqueued in this IIO until they have been successfully been written to the memory. So basically, the IIO buffer occupancy is essentially equal to the in-flight NIC to memory request at any point of time. Okay, so now when there is contention at the memory interconnect, that leads to increase in this in-flight IIO requests. Okay, because of back pressure coming from the memory interconnect. Now, if I increase the degree of the memory interconnect contention, that leads to further increase in my in-flight NIC to memory requests until the point comes where I run out of available buffers at the IIO, which leads to further back pressure to the NIC, and that's where I start to see host congestion, right? So host congestion only happens whenever my IIO buffer occupancy increases. Okay, so just a quick plot here. So this shows the measured IIO occupancy versus time for 1 second time horizon. When there was no congestion, we observed on our test bed IIO occupancy close to around 65 cache lines when we are saturating the full 100 Gbps line rate. And when there was host congestion, then it increased and saturated at a value of around 92 cache lines on our test bed, right? Now, this signal, so basically this tells us that IIO occupancy could be a good candidate to be a host congestion, an effective host congestion signal. And it is measurable on commodity hardware just by using a single MSR read, right? And these the addresses of these registers are available in Intel's performance monitoring manual. We saw that it takes less than around 600 nanoseconds to do this MSR read. So basically, it's possible to measure host congestion using IIO occupancy at sub-microsecond or sub-RTT timescales, right? Just to quickly demonstrate it in action. So this is again the same setup like earlier. Right now, there is no congestion happening. So I'm just trying to also show the IIO occupancy coming on the bottom right. So when there is no congestion, the IIO occupancy versus time is around 65 cache lines. And so now I'll launch the host local application again, which will trigger host congestion. Again, it will take a few seconds for this application to start. Okay, so my network throughput, okay, started to reduce, congestion started to happen, and we can see the IIO occupancy increased perfectly in correlation with the presence of host congestion. Okay. Okay, so now we have a good candidate host congestion signal. Let's now talk a bit more about the host local congestion response. Okay, so it can be, it's slightly involved, but I'll try to give some high-level conceptual overview. So essentially what host local response tries to do, it tries to maximize the sum of the network traffic rate and the host local traffic rate while minimizing host congestion, right? So one easy way to visualize this is using a state space representation. I have host local traffic rate on the x-axis and network traffic rate on the y-axis. And this green line that you see here shows the Pareto optimal regime where I do not see host congestion, but I'm maximizing the sum of my host local and network traffic rate. Okay. Now suppose I'm given a target network traffic rate, right? This could be set by any desired resource allocation policy by the user to meet. Then this just tells us the ideal point of convergence, where in terms of my required network traffic rate and the host local traffic rate where I want to go, right? Now, what hostAC tries to do is, depending on whichever regime I'm operating in among these four, it tries to converge to this desired regime, right? And we already know how to detect which regime we are in terms of host congestion, and network traffic rate is also measurable by single register reads. Okay, so let me try to give an idea of how hostAC converges to this desired point of convergence by varying the rate of host local traffic. So let's start with.
We have like 5 more minutes.
Okay. So let's start with the more interesting case of regime 3, where I am not, the network traffic is not meeting my desired target rate, and I have host congestion, right? So I have host congestion, so I need to reduce rate of one of these two kinds of traffic. Because I'm not meeting my network traffic rate, I reduce the rate of my host local traffic, right? So in regime 3, we reduce my host local traffic. And when we come to regime 4, because we do not have host congestion, we can increase the rate, right? Because I'm not meeting my network traffic rate, so I should ideally increase my network traffic rate. And this is implicitly done by network transport protocol in their AI phase of AIMD. So basically, we do not do anything in terms of host local response. And 1 and 2 are kind of opposite of 3 and 4. So in 1, we increase the rate of host local traffic. Okay. And in 2, we reduce the rate of network traffic, which is done by the network congestion response, which I'll show in the next slide. But yeah, now, so this is essentially what host local congestion response does, how it decides when to increase or reduce the rate of my host local traffic. Okay. And to do that, there are available mechanisms provided, again, in today's commodity servers. For example, on Intel, there is this tool called memory bandwidth allocation, or MBA, which provides multiple allocation levels. And with varying allocation levels, the allocated memory bandwidth can vary, and users can configure these allocation levels, again, by single MSR register writes. So can be done at sub-RTT timescales. And the MBA interface also, MBA basically is implemented transparently to the applications, so require no app modifications. Okay, so I'll skip the demo in the interest of time for this, and I'll quickly go over the network congestion response. Okay, so how hostAC does the network congestion response is it does not make any modification to the congestion control protocol. And it uses these host congestion signals along with the network congestion signals to perform this end-to-end response. So let me give an example using ECN-based protocols like DCTCP. So DCTCP, for example, works by switches marking ECNs whenever they see congestion. So what hostAC does is that the hosts, looking at the host congestion signals, also mark ECNs, right? And the congestion control protocol works independently. without knowing who marked the ECN, whether the switch or the host, right? And just to give an idea how this works is the host uses the available net filter subsystem. Whenever there is my I occupancy is greater than a threshold, I just mark the ECN bits in my IP header, right? And this is done before the transport layer comes in, so I don't have to modify my CC protocol. Okay, so quickly going through. So yeah, so hostess is implemented within the Linux kernel. It makes no changes to applications, host hardware, or network hardware. For host local response, we use a dedicated core right now in the prototype to get sub-RTT granularity detection and response. And for network response, we just make a few hundred lines of modification in the network stack just to mark the ECNs. And I'm happy to show the demo offline.
Yeah, we have to wrap this up now.
Yeah. So, yeah, happy to discuss more questions.
Okay, thank you very much. So we have time for exactly one question, and if you have more questions, please meet Sasham later.
I'm happy I was fast enough pressing the button. Thank you very much for this. This was very interesting indeed. There's just one element here that puzzles me a little bit, and that is why loss even happens in the transport from the sender to the receiver and the network traffic, because we have flow control for this, right? So I would expect that normally the host on the receiver side, when it sees that the NIC buffer is getting fuller, it should use the receiver window to scale down how much the sender would be sending. And that would also be the correct signal, I think, to carry in instead of ECN bits, in fact, for what you're doing.
Right, great point. So yeah, so flow control in today's TCP protocols, they are based on the receive window size, advertised receive window is dependent on the socket buffer size on a per flow basis, right? And the drops are happening at the NIC buffers. So your socket buffer sizes, you have to set them on a per flow basis to basically based on the BDP requirements. So if you have large number of flows with like couple of megabytes worth of BDP for these high-speed networks, they are large enough to keep in-flight packets so much that your NIC buffers, which are typically like 1 or 2 megabytes, to be overwhelmed.
Okay, got it. Thank you.
Okay, thank you very much, Saka. Perfect. Thank you. Thank you very much. Sorry about the trouble. I'm just bring up the slides. Okay. Yeah, so I'm very happy that, so next we have Renata Teixeira from Netflix, who's going to talk about low orbit, high impact, what we've learned from Netflix streaming over LEO. And Renata is a staff research scientist on the streaming algorithms team at Netflix. She has a PhD in computer science from UC San Diego, and many of you know her. She conducted research on internet routing at AT&T Research, and she was a researcher at CNRS Leipzig at UPMC Sorbonne, and also the director of research at INRIA in Paris. She was a visiting scholar at UC Berkeley, ICSI, and at Stanford. Her work focuses on quality of experience and measurements, analysis, and management of data networks. She is an ACM distinguished member, received the ACM IMC Test of Time Award for Paris Traceroute, and she was recognized in 2017 as a N2 Women Star in computer networking and communications, and we're very happy to have her here today.
Thank you. So, hello everyone. I'm the one who's thrilled to be here. I want to thank the organizers of IRTF and also Space RG for the invitation. As you can see, I have a red tag. It's my first IETF, if you can believe it. I know, I've been in this field for over 20 years, no need to laugh. I'm very happy to see some familiar faces and really looking forward to meet all of you and chat during the week. I'm here until Thursday, so please come by and say hi. So I'm here to talk about the work and like what we've been learning about Netflix streaming over low Earth orbit satellite networks. So let's dig in. So this work is actually from this paper that was presented at Sigmetrics earlier this year. And it's really mostly the work of Liz Zhikovic, who is a student with us at the time and now a professor at UCLA, and also with my colleagues at Netflix, Reese Engard, who is over there. Hi, Reese, and T.Y. Huang, who unfortunately couldn't make it here. I did update some of the plots from the paper, so you have data up to October 2025, so you have new data in case you have read the paper. Hopefully we can learn more. Okay, let's start. For those who don't know much about LEO, so LEO satellites work in constellations of hundreds to thousands of satellites, so you can have a high global coverage of the Earth. So you're always circling around the Earth. In the orbit of 300 to 2,000 kilometers from Earth, which allow us to get much lower latency than we would get for geostationary satellites. And also, we can get higher bandwidth with that. So LEO is here, and millions of people already using it. Starlink has recently announced they crossed 7 million subscribers globally. And there's more to come. Amazon is launching lots of satellites with the Project Kuiper, and so they soon should have their service coming to customers as well. So in addition to that, people love to stream. So streaming keeps being the biggest traffic in the internet. We have just surpassed broadcast and cable TV with streaming recently. And if you look at the latest Internet Phenomena Report, you see that like the largest traffic is streaming, the biggest traffic days in 2024, they all coincide with live sporting events. So, and I work for Netflix, so of course, it makes sense to ask the question, how does LEO affect Netflix streaming? So of course, we are interested in LEO at large, but most of the data we have today and the scale that we need for this kind of analysis comes from Starlink. So let's dig in. We actually asked a number of questions to understand this problem. So what's LEO's role in Netflix video delivery? As I show you, streaming over LEO is rapidly rising in popularity, especially in places like Africa. Then we look, the original question was interested in, like how good is Netflix on-demand streaming over LEO? And it's actually pretty good, often similar to terrestrial connections, but as I'll show you, have increased bitrate switches and also rebuffers when the playback gets stalled. So we looked into whether we can reduce bitrate switches and rebuffers over LEO. And our existing congestion control and adaptive bitrate algorithms can help partially if we tune it, but it doesn't fully get us there. So that's nice. It's promising for us. There's research to be done in this area that I wrap up discussing some of that. Okay, so let's start with the first question here. All right. So this is a plot from November 2022, more or less, up to October 2025. And here I'm putting the ranking of Starlink based on Netflix viewing seconds, okay? So as you can see, it's rising pretty rapidly. And as of today, Starlink is the 19th out of over 20,000 ISP that people stream Netflix from. So it really went up. I'm seeing the eyebrows going up. Yes, it went fast. We also saw that LEO is nice because it gives us this global reach. So we can have people all over the globe with a single ISP. And here it's from Feb 2022 to today. You can kind of see the number of countries where we see people streaming Starlink has been growing pretty steadily to get today to this almost 150 countries. There is this bump over there that I think it's just GeoIP craziness. I don't think that they lost customers and came back. That's my current analysis of this. But I mean, the general trend is true, and it's not a time, it's ties with what they say also about the number of countries that they are operating on. So which regions we see most people like streaming over Starlink? So here I'm showing the fraction of view hours, of Netflix view hours over Starlink relative to the first month we saw people streaming over Starlink in the US. Okay, so this all normalized to the same scale. And as you can see in the beginning, mostly people were streaming over Canada and the United States. And as every time there is a new launch of Starlink in some place, you see these large jumps there that sort of represent, okay, you launched the service there. And it's kind of interesting. So US and Canada kind of kept up for most of to 2024, but then Latin America is picking up. So now it's the second. So if you look at today, it is the second area that people stream the most, Netflix over Starlink. Here's a different way of looking at this data, where we're looking at growth. So again, it's over time, and you're dividing the view seconds in a month by the view seconds in the previous month in the same region. And I mean, you see the similar spikes that we saw in the previous plot, and Africa kind of dominated for most of 2024 in terms of growth, but now all of the regions are converging. So it kind of sees like the market has is more stable now. So it's just the big launches have gone, and now things are becoming more stable. Okay, so what we've learned in terms of LEO's role in Netflix delivery, we see that streaming over LEO is rising very rapidly, and it's helping expand Netflix into some new areas. Just as an anecdote, I went to Easter Island with my family, and like a few years ago, and everybody tell me, oh, now we have Starlink, so we can have Netflix. And they were watching it every night. It's great. So it sort of helps some of these areas that are less connected, they now can have these kinds of applications. So LEO has some known challenges from prior work. So because we have this low orbit, so a satellite is going to circle Earth in about 90 minutes or so. So that comes with very high variability. So what do we know about Starlink architecture? And just to give us some context, so we're all on the same page here. So starting from the, I guess, right side for you, you have the dish in the customer's home. And then that dish is going to be connecting to a satellite that's passing over on the sky. So it kind of steers electronically to connect to the closest satellite. And from the satellite, the traffic will then either cross some inter-satellite links or go directly to the Starlink gateway, so at the ground station. Okay. From that point, it will go to the point of presence and then over to the internet. So if you think of where Netflix's contents are going to be, our servers, they're either going to be in the point of presence directly, because they're often very close to the users, or in the first exchange point. So we're pretty close to the user just after the satellite link. And one thing that's also important for the context here is that Starlink reconfigures its network at every 15 seconds. So every 15 seconds, the lasers might be misconfigured, the satellites, which ground station they're using is going to be reconfigured. So things are going to be changing pretty fast, okay? And some prior work has been looking into, okay, what's the effect of these changes into network performance? So I like to, because Jorg invited me, so I have to show one of his papers here. So from this paper, we have these two example locations when they're looking into RTT from these two different locations. And what's striking, I mean, people who have looked at RTT data, we know that it varies a lot. So that's very typical from things we see in the internet. What is unique in the Starlink time series that you're seeing here is this 15 seconds baseline shift that you're seeing. Because at every 15 seconds, you see there is this, the baseline itself is changing. That's because of these reconfigurations. And you see that the change happens at the same time for both locations, because it's a global reconfiguration that's happening in that network. Okay? We also see periods of high loss. And what's happening is, so let's say you have your dish connected to satellite A, and then it's going to change to satellite B. And what it's doing is a hard handover. So the packets during that period are going to be lost. Another thing, so this is actually Liz's paper, one of my co-authors. They were looking into how location affects the RTT variability that you're seeing. So these are different Starlink pops. And there are a few things that are striking very quickly. So for instance, if you look at Mexico, the RTTs are like 10, 20 milliseconds, whereas Brazil or Nigeria, it's much higher, both the average RTT and also the variability in that region. And multiple things will affect that. One, just the satellite coverage itself, like depending on the latitude, you have more coverage of satellites in certain locations versus others. Also the difference to the base stations, the ground stations. And even so, talking about latitude again, so in some locations, the satellite's going to be more just directly on top of you, whereas in others, more towards the horizon. And so there is more line of sight, like there's more obstruction perhaps in line of sight as well. So there are lots of things that can explain the mix that we are seeing here. But this variability in terms of location is something that's very typical. And we see that for packet losses as well, both the spatial and the temporal variability. Just a second.
Yeah.
All right. So what this prior work tells us about LEO, we see these reconfigurations at every 15 seconds, there's periodic shifts in latency, losses, and large variations over time and location. So you might be asking yourself, so is this LEO or is this Starlink? That's a very good question. So there's some things that we're seeing here, like 15 seconds of reconfigurations. Of course, that's Starlink's engineering decision. And there's hard handovers also, Starlink engineering decisions. But the fact that we have this high mobility, that we have handovers, that we have reconfigurations, that's going to happen with any LEO SP we see. So some of these things are definitely going to generalize across. And so we should be thinking about that as we design protocols. So how good is Netflix over Starlink? So we use a number of metrics to measure quality of experience. The overall video quality is like how look the video image is, whether there are switches in quality, like the bitrate is switching over time, whether there's stalls, so the rebuffers, so playback gets stopped, and play delay. So here I'm just going to talk about the first three, and you can read the paper if you're interested in play delay. So at Netflix, we use VMAF, which is the Visual Multi-Method Assessment Fusion, to predict what a user would say the quality of an encoded image is. Okay, so at the same bit rate, if you have a very simple scene and animation, for instance, you can have a very high score, whereas for that same bit rate, if you have a more complex scene, like an action movie with lots of movement and details, then the score might be much lower. Here, I'm actually showing an example of two rungs of the bitrate ladder. So this is like the lowest quality we would offer for this particular video, and it's a standard definition resolution, and it would have a VMAF of 10. And here is a top quality with 4K, 23.4 megabits per second bitrate, and that's a VMAF of 107. So you can kind of see that's how we're rating quality. So here I'm showing that LEO actually delivers comparable quality to other terrestrial ISPs in the same market. So for each bar here, for these countries, I'm just comparing the Starlink with non-Starlink ISPs in the same market. So for Mexico, when you're dividing the quality, you see that it's a little bit lower Starlink than others, but it's mostly close to 1 for all of these different markets. Okay, so the quality, like if you look at the perceptual visual quality, it's pretty decent. In some places, like Malawi and Zambia, is actually better. So the value is going above 1. So Starlink achieves better quality than other ISPs in that same market. So that's good. We have good quality. But we see these things online. People are complaining, wow, the quality is varying a lot. There are a lot of bitrate switches. And we went to look into our data. Is it true? Are we seeing the same? It's true. It is true. So we do see, so if you do, so here I'm showing you the distribution, the CDF, of just the sessions where we had switches and comparing Starlink and non-Starlink. So this distribution comparing the two, and here's the % additional switches that we saw over Starlink and all the other ISPs. And you can see that here we have about 200% more bitrate switches for about 75% of the cases. So we do see, in fact, more switches. And why do we see that? So what's happening is that we see switches because of the throughput is fluctuating over time. So here are two examples. This is not Starlink, this is Starlink. And the red dotted line here, it marks 10 megabits per second in both of the plots, okay? So you can see two things, two differences between these two plots. One is the throughput here overall is lower, and it's fluctuating more into this range here of 10 megabits per second or so, which is more relevant for us because that's the area where we have our encoding bit rates for a bitrate ladder. Whereas here, I mean, if you have this big spike at 100 going to 40, that's not going to cause a switch because that's much above the maximum bit rate in our ladders. And the second thing we see is that when you have this dip, it takes longer to recover. That 15 seconds is still there. There's reconfiguration, 15 seconds. It's also impacting here. Just to look into the distribution factor of comparing Starlink and non-Starlink is the blue line, and the orange line is Starlink with the top 10 most popular ISPs that people stream Netflix from. And then I'm showing the CDF again, and what you see, because we're dividing Starlink with the others, so if they were similar in terms of throughput, everybody would be in the one line here. But we see that overall, Starlink is lower. So we have lower throughput over Starlink than in the other ISPs. Okay, so now moving on, we also see that people complain about rebuffers. Not only with us, also for YouTube. Do we see more rebuffers? Rebuffers, just to put it clear here, they're very rare. We don't have many rebuffers, but for across all ISPs, including Starlink. But when they do happen, it's over 200% more likely to happen in Starlink than other top 10 ISP, if 40% more than non-Starlink. So why rebuffers are more likely on LEO? So this plot, what we're looking into is like where in the bitrate ladder was our ABR when we saw the rebuffer. So here, 0 is like the lowest quality possible. So if you're already at the lowest quality possible, there was no other thing to select. We had to rebuffer, okay? And we see that for Starlink, we are more often already in the lowest quality possible when we have a rebuffer. So there are two things that can be happening. So we're already at the lowest quality. So either we downshifted, we went down too late, and we look into the data, and it's true that we spend less time at the lowest bit rate for Starlink than for other ISPs. And two, maybe there was like a short outage, and then we didn't have enough buffer to mitigate. And we also see the same thing, that for Starlink, we have more outages than for other ISPs. So this is what's causing us to rebuffer in this case. And here I'm just showing that overall, like Africa and Latin America have 2 to 3 more rebuffers on Starlink than US and some of the other regions. Okay, just to summarize what we learned in terms of the KOE for LEO. And we see the quality in terms of video quality, is pretty comparable. And in some cases, some small islands in Africa, we actually have better quality than some of the local alternatives. But there's this trade-off where we saw more bitrate switches and also rebuffers. All right, so can we do something about it? Can we reduce the bitrate switches and these rebuffers? I mean, we have two levers to play with like these dynamic network environments. One is the congestion control, which is controlling the send rate in the network path. And the second is our ABR, the adaptive bitrate algorithm, where we are choosing which video representation, so the resolution and bitrate, that we're going to be fetching. So here we directly kind of lower the traffic that we are requesting. For congestion control, we tried a less reactive congestion control using multi-CP. So for every act byte, we are increasing the congestion window by 3 bytes. But then when we saw a loss, we were just decreasing it by 1. So we're being less reactive on loss. This helped increase the throughput. Remember that Starlink had lower throughput? It helped to increase it. And we got like smoother streaming, but then we had too many retransmissions and higher latency. So that's not something that we wanted to deploy. So tweaking just our TCP Reno and like tweaking it a little bit can help, but it doesn't fully recover the high variability that we get with Leo. Because we keep having like, okay, you have more throughput, but then you have more queuing and more loss. For adaptive bitrate, we tried tuning our standard ABR parameters. So for instance, like the throughput discount. So if I'm measuring 10 megabits per second, and I have a discount of 50%, then the maximum bitrate I can pick is going to be 5 megabits per second, okay? So we tried tuning a bunch of this. It helped somewhat, but again, it didn't help close the gap with terrestrial ISPs on the switches and rebuffers. So the main issue is that our ABR, we're using these point throughput estimates, and that's not really good for this highly variant environment. So you're probably frustrated about the details because I didn't really show much in the last 2 slides. So if you are, I invite you to come on Thursday morning to the Space RG, where I'm actually going to present the 2 things I just talked about. So please come and join us, and I'll be happy to discuss more there.
Thank you, Galata.
Are you good? No. Sorry.
Thank you for the advertisement.
That's the advertisement. I hope my timing is right. I looked at the agenda.
You're okay. You're okay.
Okay.
Sorry.
Okay, it's okay. So now just I wanted to wrap up. Almost ready. I wanted to wrap up with a few questions that we still have in terms of, okay, what are the research opportunities I see for LEO streaming? Just to be clear, there's probably a lot of interesting research in like the LEO networks themselves and the physics and the satellites and having distant talks with multiple satellites, but I'm not an expert on that, so I'm going to focus on the follow-up from the research we've done. So first, we would like to look into, so video streaming in a way is like the best case scenario for these highly variable networks because we have really large buffers, we can tolerate this short-term variability. But now we are into live and gaming, and so these are much more challenging because of the sensitivity to jitter, loss bursts, and almost no buffer. So we'd like to start looking to see, okay, what does LEO mean for these new applications? For the adaptive bitrate and congestion control, of course, they will need to evolve for LEO. For congestion control, I think we need to be in a world where we expect the bottlenecks to be moving and to live with non-congestive losses. So we need to change our mindset. So people have shown that rate-based control, in particular BBR, seem to work the best for Starlink. And we've been playing with pacing at Netflix, and it does seem promising. So that's something to keep in mind. We also seen people working on like having LEO-aware hints to the end host. I'm not sure that's my favorite thing, because I'd love to have something that's completely agnostic and just work, but I think we should all be part of this discussion. And for adaptive bitrate, I already kind of gave the idea that I think we need to kind of work on our throughput prediction and be more variance aware, I think. So that's sort of where my head is right now. And given I'm at IETF, I thought like, oh, what we should be thinking about in terms of a community. So if we decide to go for this, having the network give us hints, maybe that's something we need to standardize, like maybe things like, oh, we're going to reconfigure soon, or we have this stability window now, so use it as much as you can. I also think the community should invest in better testing and benchmarks for more reproducible evaluation over LEO networks. And don't ignore LEO. So if you are building network systems and applications and protocols, there are lots and lots of people that are using LEO now. So keep that in mind as you're testing or proposing new things. And as a final message, I wanted to leave you, of course, with a Netflix movie. What am I here otherwise? I had to, no? So I don't know if you guys saw this, but the scientists, it's a good movie, huh? I agree. And so scientists are looking up with the danger of this comet that's hitting Earth, and they are looking desperate. I want us to actually look up together with hope, because we have this new technology that is covering more and more, can help us bridge the digital divide, and there's really, really cool research problems around it. So thank you very much, and here's my email, but I'm happy to take questions now as well. Thank you.
Okay, now thank you very much. Okay, we do have time for questions, and let's just get started. So James is in the queue.
All right. Thank you very much, Zara, for that.
Yeah,
okay, can you hear me?
Yes.
All right. So thank you very much for that wonderful presentation. And I think it couldn't have come at a better time, because this is a new technology that that's quite fascinating, so to say. However, I have a couple of questions for you. I'm from Nigeria, by the way. Okay. All right. So I really want to know, because the other time when you were making your presentation, you showed a data as per the buffer rate in some African countries higher than the other ones. So you perhaps, because of time, didn't dig deep into why we have more buffer in those African countries than the other countries that you were comparing with the African countries. Okay, so I want to know perhaps if your research dug further, and peradventure, what are the reasons for that? That is one. Then the second issue I want to clarify, it's actually on the issue of quality of experience. I'm aware that we have quality of service on one hand, and of course the quality of experience. If you talk about the quality of service, oftentimes you look at the technical parameters within the network itself, and it looks more to me like your presentation focused more on that, right? Compared to quality of experience, which of course is, what word am I going to use now? Subjective, right? Mm-hmm. And sometimes when you want to talk about quality of experience, you may need to talk about mean opinion score. The way I perceive it, the way he perceives it, the way another person perceives it, bring everything together before you can now say, okay, this is the quality of experience. So I'm just trying to balance the two, because you focus more on, some technical parameters and all of that. And the last but not the least, sorry, I didn't hear so much about jitter.
So sorry, we have many people in the queue, and we
this is the last one. I'm wrapping it up now. I believe jitter may be maybe something to talk about in this issue. I heard so much about latency, right? But jitter, actually show us the variation in delay in the delivery of the packets, which of course can be adduced to the fact that, okay, you may need to look at how you prioritize real-time data, real-time packets. That is on one hand. And on the other hand, you may need to now start to look out for other issues. So please, can you just clarify all these things? Thank you.
So for the first one, the rebuffers, it's similar like what I was explaining for RTTs and losses. It varies a lot over because of the location of the ground stations. So Starlink, they have been improving their network and putting more ground stations, but they didn't have many in Africa before. And so that's one issue. There's the issue of the latitude I was saying. There's the issue also of the different types of customers. Like some customers, like maritime customers, they do experience like higher latency, they experience higher losses than some of the stationary customers. And it depends also on the utilization of the network. So all of these things will combined cause more issues in places than others. For the KOE, I would have to talk to you about that offline. VMAF is actually a model that's based on quality of experience, like the MOS measurements, but it's a model. It's not a direct question. And for jitter, it's something that I really hope we're going to be looking more into if we look into live and cloud gaming.
Juan Freire from INRIA. Thank you, Renata, for this very nice presentation. I have one concrete question. Are you or were you able to discriminate which of the performance metrics you obtained were obtained from cases where the satellite was operating on bent pipe modes on every terminal satellite ground station versus the case where the streaming actually flies over inter-satellite links?
We don't have that information. Everything we have is sort of based on the client logs or the server logs. So it's very hard to have that detail. Yeah, that would be very interesting to know. Yeah.
Rajiv.
Hi everyone, Rajiv here, wearing my hat as an SVTA member over here. So I find this presentation quite interesting. Unfortunately, I'm coming here from the CDNI meeting, which thankfully ended early, so I was able to catch this without having to listen to a recording. But one of the things that stood out to me was the fact that you are talking about the impact of things like the congestion control mechanisms and how they can potentially impact the viewing experience by controlling things like quality ladder switches. So one of the interesting projects that we have been running recently in the SVTA is we've been evaluating the performance of different congestion control algorithms um, on different styles of network environments, okay, as a part of our analysis of quick, okay, basically comparing quick with http2. And obviously we try to simulate different types of network environments with different losses, different latency parameters and stuff like that. It would be very useful if we could get a typical LEO network connection profile, which says, hey, over millions of sessions, a typical LEO network connection behaves like this, with this kind of latency, with this kind of jitter characteristics over the life cycle of a media playback session. And that can then be used by people like us to plug in when we are doing these kind of research activities. So, we obviously love to collaborate on this and see if we can build some better testing of congestion control and potentially optimize them for LEO style network environments.
Yeah, thank you for the question. I mean, I kind of evoked that in some of the research questions. There are simulators for LEO, and there are some test beds where you can run things over LEO, but I agree with you that it would be very nice to have a benchmark that everybody could use the same and we all talk the same language. Hopefully, as a community, we can all work together to get there. Yeah.
Sounds like a good topic for Space RG.
Exactly. And I mean, I'll be talking about our congestion control results there. So yeah.
Last second, I'll be fast. So thanks for coming. Great talk. I hope you come again soon and don't wait another 20 years. So actually, this is an easy one because it's not really related to your talk. It's like we found it difficult. We like in the IETF and in general in research and in engineering, we find it difficult to talk to Netflix, not to Netflix, sorry, to Starlink. We find it easy to talk to Netflix. You're right there. I'm doing it right now. No, sorry, it's been a long week. It's Monday. Starlink and other providers of these constellations, and I wonder. I mean, you have sending them a lot of traffic, so I wonder if you have a better angle to talking to them, and whether we can somehow use you and others like you to maybe get them here occasionally so we can have a conversation with them. Because I see lots of papers where you measure things and then you try to infer what might they be doing, but it's difficult for researchers to get ground truth, right? Have you been lucky? Or
so they've been nice, very nice, helping us with this research, and yeah, I'll be happy to put you in contact with the folks I know. Yeah.
I'm Stuart Cheshire from Apple. I think we're out of time, so I'll make this very quick. It's more of a comment that we could discuss later. I noticed on one of your earlier slides, you talked about packet loss during the handoff, and I was curious to see what you were going to say about that, because you could say that it's Starlink's job to avoid that loss. And if they do a handoff, they have to reroute the packet so they get there. Or you could take the view that it's fine for Starlink to lose the packets and it's the end system's job to deal with that. And I found the answer when you talked about non-congested losses. My observation there is I've been hearing this pretty much my entire career in networking, that what is wrong with TCP is that it slows down when there's packet loss, whereas a Manley protocol reacts to congestion by doubling its data rate to power through the congestion. And I'm involved right now with a home automation protocol that runs over IP. I won't say which one. And they don't use TCP because they don't want to slow down when there's packet loss. They want to power through by redoubling the transmission rate. And they've managed to recreate the congestion collapses of the 1980s, where once the network gets overloaded, it goes into a death spiral of ever-increasing retransmission and it never gets out of it. So I think it would be great to explore this area and give some guidance, because if you are going to accept that loss doesn't mean congestion and you should respond by retransmitting really quickly, you got to be really certain that it wasn't an overload condition.
So just yeah, to comment. So I think that there are things that they can do to get better at not having this hard handover. And I think if the physics works, and they're probably working on this, they will get there. So hopefully things are going to get better. One other thing that we've seen with our local experimentation we are doing is actually if you increase the rate, the bit rate you're sending, you also increase your loss rate. So sending more is not good here. So we need other solutions.
Thank you.
Thank you.
Thank you very
Thanks,
much.
everybody.
So we are out of time. Thank you very much, Renata, and also thank you, Jake and Sakon. Thanks all for coming. Don't forget Space RG later this week.